And hello everyone, how y'all doing today? It's me again. And today we're gonna talk about a little bit about surface roughness. So what then about surface roughness? Yeah. So in the last few videos we were always talking about wall functions, and we'll have this law of the wall which we're talking about, where this dimensionless, what do you call that? Dimensionless velocity will vary with dimensionless distance from the wall, either using some Van Driest model or some other experimental model. Yep. So, and we also talked a lot about, how Van Driest, the inspiration from Van Driest model was used for LES modeling. So that's some of the background that we have been talking about for turbulence modeling. And now to the next step, to lead us on another so-called wild goose chase, but not exactly wild goose chase, but very important bit of turbulence modeling. Yes, we know wall functions are important, right? So you can see, okay, yeah, wall functions are important, and this was all our stuff from the last video. Come to think of it, this looks like a very nice background, but anyway, so we have wall functions, right? Wall functions. We saw how it was done for the Reynolds average Navier-Stokes. We saw how it was done for the Smagorinsky model. LES model, large eddy simulation. Alright, so far we have talked about a law of the wall. Okay. Alright, a law of the wall. And this begs the question, we've seen this thing called the Reynolds, Moody chart. We've seen the Moody chart before. If you just take a quick look at Wikipedia, okay, or you take a look at Engineering Toolbox. So I'm going to paste a lot of this inside our video description, a lot of the links, so don't worry about it. Just pay attention to what I'm saying. Yeah, if you look at this Moody chart, we would know that yes, in laminar flow we will have one certain regime of flow where the Reynolds number is kind of constant, or rather the friction factor varies linearly with this Reynolds number as well, right? And then in the turbulent regime we see this interesting network of lines where we have varying degrees of turbulence with increasing Reynolds number, and then we see this very important bit called relative roughness. So if we were to correlate what we were doing in the last few videos, we were mostly doing smooth surfaces, right? The law of the wall that we were dealing with was mainly dealing with this bottom curve, which deals with smooth surfaces. Okay? So what we have been talking about deals with smooth surfaces. Alright? In LES modeling, it's kind of different because you would pretty much want your mesh size to be so small that if your surface was rough, you would fully resolve the velocity profile so that you'll capture most of the eddies in this region, okay, in the boundary layer. Alright, you make your mesh size small enough to capture the velocity fluctuations within here. Of course, you kind of filter some of the velocity out as we are talking about before, but in a large eddy simulation model, you would resolve this roughness. Resolve our roughness. That's the general thing, because you want to kind of model some of the eddies in that region. You have to make your mesh size really, really small, and that will of course mean that you have to have a very good mesh and a good computing power. So of course, yeah, in LES this is what you do. But let's say for Reynolds average Navier-Stokes, the basic Reynolds average Navier-Stokes, we still have to model it. We already did so with smooth surfaces, and now we want to talk more about rough surfaces. Okay, so what do we do with rough surfaces? How does it change this wall function or law of the wall? So the main thing, okay, I would like to bring you to is this paper, okay, and this is called Accounting for Wall Roughness Effects in Turbulence Models. So it's called a wall function approach. If you just search this in Google, okay, you just take the first, well, according for my Google search, it is the first result. So this is what you get: Accounting for Wall Roughness in Turbulence Models, a wall function approach. This is in the 7th European Conference for Aeronautics and Aerospace Sciences. So it is a conference paper, it looks like. Okay, and it's pretty useful for what we want to do. It's very relevant. You just scroll down to this second page where it says Roughness Correctness Principles. Then you will see this little picture here. Now this of course shows that we have our same log law region. If you can still remember, in the last videos we're talking about the U plus and Y plus. Okay, so we'll have this U plus, Y plus, or is it the other way around? I need to take a look again. Law of the wall. Yeah. So U plus is plotted against Y plus. So as follows, and then you have this little curve here. So you have the linear region and then the log region, and of course your curve will go something like that. Okay. So this region is the U plus equals to Y plus. Okay, U plus equals to Y plus, and then here we'll have the log law. And it appears from what we are finding here, this roughness affects the log law region. So roughness affects the log law region. Okay. Okay, roughness affects the log law region here. Hope you can read the handwriting. I apologize if it's too rough. Okay, so anyway, so you have this basic function here. U plus equals to 1 over kappa ln Y plus, which is great, plus C. This is very much what we have talked about before, right over here in the last few videos. Okay, so we have a log law region over here, 2.5 ln Y plus 5.5. So 1 over kappa here is 0.4. 1 over 0.4 is about 2.2. So I just do some quick Excel for you. Equals 1 divided by 0.4, and that will give you about 2.5, not 2.2, sorry. So this 2.5, all right? Yeah, so this 2.5, yes. 1 over 0.4 is 2.5. And then you have a 5.5 here. And what we have for this roughness is that you have this delta U plus function. Okay, delta U plus function. All right. And that will take into account the roughness. So let's see. Where is the paint? Yeah, this is log law region. Your vanilla log law, your default log law. Okay. Okay, default is u plus equals to 2.5 ln y plus, and this is the normalized for friction velocity, of course. If you've been looking in our other videos, okay, u plus equals 2.5 ln y plus 5.5. Alright, so that is our default. Now, if the surface is rough, then you would have something like this. U plus equals to 2.5 ln y plus plus 5.5 minus some delta u plus. So you can see that for given different values of this log law, for different values of this u plus, this curve can shift downwards. So I can like shift the log law downwards by varying degrees, of course, but it will still look linear on this log law chart, basically. So it may or may not look linear. It won't look linear on this chart. Okay, but the effect is that you kind of shift this curve. You shift this curve up and down by adding or subtracting this u plus factor. Okay, so this, remember, this is a log scale, log plot. Okay, so that's why it looks a bit funny. Now, of course, the question is, what is this? What is this u delta u plus? And then we kind of take a look at this paper and we find that this delta u plus equals to 1 over kappa ln 1 plus hs plus over some exponential 3.52k kappa. So what is hs plus, by the way? hs plus is this. hs plus equals to some height of the grain, okay, some equivalent sand grain height, they call it equivalent sand grain height. So it's the equivalent sand grain height, and then you kind of non-dimensionalize it using the friction velocity and of course the viscosity, the kinematic viscosity. So friction velocity, I will just use v star to annotate it here. Okay. Yeah. Let's see what. Oh, okay. I used u star before, so let's stick to u star, not v star. U star, and I'll have a new over here. So this is hs. Okay. So great. We know what this is. We know what this is. And what is this? Okay. We want to know what hs plus is. Okay, and where does it come from? How can we trust this data? And more importantly, of course, how does it relate to this Moody chart? Where's this Moody chart? Yes. How does it relate to this Moody chart? So for that, we'll need to take a look at how this relation actually came about. So the shift delta u plus, it says here, the shift delta u plus can be explained in a more compact form by Gregson as blah blah blah. So where does this data come from? It comes from this whole plot here. Now let's digest this slowly. So basically, it is saying that originally we have this kind of correlation. U plus equals 1 over kappa ln y plus over hs plus. Okay, so we have a u plus as a function of y plus, but hs plus also comes in. Then we have a extra b over here. So it is not exactly the same as this kind of a form, but it is an empirical correlation. And here we go. U plus equals to 1 over kappa ln y plus over hs plus over HS plus a big B. Okay, question is, what is this B and how does it change? So where you have this first case, HS plus goes from 1 to 3.5, B equals to blah blah blah. 5.5 plus 1 over kappa ln HS plus. This is all fitted to experimental data, so there's no real theoretical background to it, except of course you do this non-dimensionalization to help us make it more general. Then you have HS plus from 3.5 to 7. The factor B is 6.59 plus 1.52 ln HS plus. 7 to 14, HS plus means a B of 9.58. 14 to 68, B becomes 11.5 minus 0.7 ln HS plus. For HS plus bigger than 68, B equals to 8.48. Alright, so this is where this comes from. And okay, where does this data come from? It comes from Nikuradse's paper over here. Who is Nikuradse? So if you do a quick search online, alright, Nikuradse is Prandtl's PhD student. Prandtl being, where we get our Prandtl number from, is one of the fathers of aerodynamics or something. So he's pretty smart guy. Both of them are, and they are from Germany. And a fun fact for you, Prandtl was alive and well during the Nazi regime. So he kind of got himself entangled with Nazi Germany. So which is an interesting fact in itself. You can go look it up, what this thing is about over here. Okay, yeah, this is just trivia, so you can take a look at it. I can paste the link for you. Yeah, I put it all the way at the bottom. Okay, no. Yeah, but this is pretty interesting because we always think of scientists being not politically involved, but in this case, this is it shows otherwise. Okay, so I have this. So Ludwig Prandtl and the growth of fluid mechanics in Germany. You can download this paper, or you can at least look at the abstract. So this guy is called the father of modern aerodynamics. But yeah, so look at this guy, Blazes. So these guys were taught by Prandtl, the Blazes guy, Carmen. Oh yeah, and Prandtl founded the aerodynamics Versuchsanstalt. Okay, my German, no, it's not so good. I better brush up the German bits. I don't know how to pronounce it properly. Kaiser Wilhelm Institut für okay, never mind, I'll stop. Anyway, so yeah, he founded this in Germany, and basically if you read this paper, he's been pretty involved with Nazi Germany. He may have said statements that we may not want to agree with, but I mean that's his history. So it's just an interesting thing to add to the character of Prandtl. But that's just trivia for you. Just leave in the comments. Kind of makes the learning a little bit more interesting. But away from the science history, I will get back to the actual science or the engineering bit. So if you look at Nikuradse's paper, we can find where all these things came from. They came from his own experiments. And of course, the most important thing is that we want to see whether this sand grain height, HS, this sand grain height, is it the same as this roughness that we see in here, in this Moody chart? We have this relative roughness in this Moody chart. All right. Yeah. You have this Moody chart, yes, relative roughness, okay. And then we know that, of course, there'll be some table. There'll be, okay, if you look at this absolute roughness for some common materials in engineering toolbox, you will see that, okay, we have a relative roughness in millimeters, or 10 to the minus 3 meters for certain materials such as PVC, stainless steel, from wood stove, concrete, etc., etc. All these are being used to calculate our friction factor to do this Moody chart, right? That's the roughness that we are used to. Is that roughness height in mm here the same as, let's say, this HS, this equivalent sand grain height? So to find out, we have to look at Nikuradse's paper. If you scroll down to citation number 13, okay, you go to citation number 13 all the way at the bottom. Okay, citation 13 and 14, it says, okay, this is in German, but more importantly, you can see this law of flows in rough pipes. So again, you Google this. Okay, let me close that. Google this, and the first link you will find is this NASA page. You click on that, and then you will see this page here, and then you can just click View Document. It will open a new tab, and it will give you this document here. So it's loading. I'm not going to load this again because this is pretty big. I'm just going to cancel this, and I'll show you what the document looks like after it's been loaded. And this is Nikuradse paper. It's ancient stuff. You can kind of find it in a typewriter format. And this is where you'll get it. And of course, again, the where you find that he's Prandtl's PhD student. He says here, I wish to express my sincere gratitude to my immediate superior, Professor Dr. L. Prandtl, or Ludwig Prandtl, who has all times aided me by his valuable advice. So yep, he's a PhD student of Dr. Prandtl, or Professor Prandtl from Germany. Okay, so in the next video, I'd like to go and take a look at this paper a little bit more in depth manner, and then I'll at least glean some of the important concepts from it and see whether it is what do you call that? Yeah, see whether this HS, which we were talking about earlier, HS, oh, this one's not the one. This HS over here. Alright, HS, come on, come on. Where are you? Yeah, there you are. Okay, this HS, sand grain height, is it the same as the surface roughness over here, which we will use here? Can we just use this value, plug and play into that equation? So more on that in the next video. And what's really helpful is to see this paper by Nikuradse. Okay, so I'll stop for now. I'll see you guys again next time. I'll post some links in the video, hopefully to help with your learning. And yeah, so okay, this is probably what I can just copy and paste. Accounting for wall roughness models, that's the first one. Oh, of course, yes, an interesting video for you. This guy, Fluid Mechanics 101, his channel is really good. I learned quite a fair bit from him as well. Yeah, I do my videos a little bit a different style from him, but he's a really good resource. He gives really good resource. Very nice person. Yeah, at least in the way that he puts up videos for you. So that's one of the ways. If you're interested in open foam, I can give this to you, but maybe in the next videos. Okay, and then of course we have this. We have this I say the sand grain height is an estimate of surface roughness, but is it the same as the roughness in the Moody chart? Okay, so blah 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 blah. I'll just copy and paste most of these things here, and there you go. So thanks for watching. I'll see you guys again. in the next video. Bye bye.